Terrific. Okay, Yorgos, very excited to hear you speak.
Excellent. Thank you very much, Sam, and thanks a lot to all the organizers for the invitation and this opportunity. I want to talk about some recent work that we have submitted with Andrea Beltazzi, who unfortunately is not in academia anymore, but is helping very much with the revisions. So and it's always a pleasure to work with him. And this is some work that to some extent follows work that I did during my PhD. And it tries to create a framework of using time-changed processes in the context of MCMC. So this is very much an MCMC talk. And the idea is that we're trying to create a general umbrella system in some sense to incorporate things that can be seen as time-changed Markov processes. The original, in some sense, part of the motivation was to make algorithms that can work a little bit better on heavy-tail distributions, but also on multimodal distributions. And okay, I will get to that. As I said, the goal is MCMC. So just to set up some notation, we're going to be targeting a density pi, which for the purposes of this talk, let's say that it lives on RD. So if you're a Bayesian statistician, your parameter space in this case is RD, and you have a posterior, for example, pi that lives in there. And typically MCMC algorithms, well, an MCMC algorithm is typically a discrete time Markov chain, which converges to pi as the time goes to infinity. But recently, there have been people that have been working with continuous time Markov processes instead. So in this particular talk, we're going to be taking this case, and everything that we will be talking about is about continuous time Markov processes. So we will have a process YT that targets pi, and by sampling from YT, effectively you can create approximate samples from pi. Now, it's very classic that most MCMC algorithms have problems on heavy-tailed and multimodal targets. And in this talk, we're going to suggest a general framework that will allow these algorithms to speed up or slow down in various areas of the space. This is what time changing essentially amounts to. It amounts to changing the speed of the process and speed up or slow down in various areas. Okay, and it follows up some work that I had done in the past. So just to explain some motivation, why might we want to do this? Let's say that we are in a multimodal setting. So this could be our target, for example. It's quite classic that a local algorithm, an algorithm that doesn't have very big jumps, for example, it might start from here, and it will think that the target is a Gaussian distribution, this one here, whereas in reality the target is a mixture of two Gaussians, multimodal. The algorithm is going to think that the target is just one Gaussian, and it's going to explore this one very well, but it's never going to, it's going to fail in finding out the other mode here and explore the other state space. And the reason for this is that there is this wasteland here, which has very low target density, and it's very difficult for the process to move across this wasteland here and go from one mode to the other. And there is also another problem in other situations, in situations where you have quite a lot of mass at the tails, where the mass decays less than any exponential distribution, for example. What tends to happen is that you're doing sampling, so you need to explore this mass, this significant mass at the tails. But it takes a lot of time for the algorithm to go to the tails. And then after that, it takes a lot of the time for the algorithm to stay a bit at the tails and then come back to the mode. So there are quite a lot of, there are infrequent and very long excursions to the tails, which create algorithmic instability, effectively. So this is another thing that, this is another problem. And our idea is that maybe we can try to get rid of some of those problems by adjusting the speed in which the algorithm moves around the space. Now, I'm not going to suggest that we solve the problem, by no means, but what I'm going to suggest is that what we will be talking about can be seen as a synergy, can act as a synergy on whichever algorithm is your favorite algorithm already, and it can, under some circumstances, improve its performance. I think this is what this work is about, essentially. Let me explain what the setting is. The time change process adjusts the speed of time of a base Markov process via a state-dependent function. This has two ingredients, basically. Ingredient number one is a well-understood base Markov process yt, time homogeneous. This can be your favorite process in the world. It can be some Hamiltonian dynamics. It can be some underdamped Langevin diffusion. It can be a piecewise deterministic Markov process, as we will see in a bit in this talk. I'm going to assume that this is your favorite process in the world, so you have studied it already very well, and we're going to act upon this process, basically. And we're going to apply a time transformation on this process, which is going to be regulated through the speed function S. So we're going to have the user will have decided on a particular speed function S, which depends on where the process currently is, and takes positive values. And this basically gives you the speed of the process. It gives you how quickly the process is going to move around when it is at the particular point in RD. When S is large, the time will accelerate. When S is small, the time will decelerate. And the definition of the process is as follows. We have the base process y, and now we define the time change process x, which at time t is equal to r at time t. So r is a transformation of time, and it is given as an integral of s over the path of xu du. So I just want to take a moment here, and I just want to say that this is kind of an implicit definition, because x depends on r and r depends on x as well, but it depends on x through the past, right? R at time t depends on x through everything that has been defined up to that point. So it turns out that this is a good definition. One can define this like this. And the reason why one defines a time change process like this is the following. And this is an intuitive calculation. There doesn't have to be a derivative with respect to time t, but let's, morally speaking, if we were to consider the derivative of x with respect to t, we would be able to do a chain rule here. We would be able to take the derivative of y. So x is y at rt. So we would be able to take the derivative of y with respect to the natural time, r of t, of y, and then the derivative of r with respect to t. And this is just the natural speed of y, whatever that is. And dr over dt, by the fundamental theorem of calculus, this is equal to s. So what does that mean? This means that the derivative of x is whatever the derivative of y is times s. And in particular, let's say at time 0, we can get that the derivative at 0 is y at 0, y prime at 0 times s of where you are at x0. And then the time is, the y is a time homogeneous process, so you can set any time equal to 0 and start again. This basically means that the derivative of x is s times faster than y. And furthermore, this means that x is going to follow the path of y, but does so s times faster, effectively. So you can imagine a process that lives in R2 and moves around the space. This is y, and then x is going to move on top of that path, but it's going to do so with a different speed. This is a difference. By the way, feel free to ask any questions you want and interrupt me, and yeah, of course, ask any questions you want. I have some sort of a visualization of what is going on. It's not an exact visualization, but it can kind of give us an understanding of what's going on. Let's say that this is the path of y here with respect to time t. So this is a one-dimensional process. It moves on the y axis, effectively up and down, and this is the time change process. Let's say that in this particular case, the function s takes large values in these areas here, in high areas of y's, and it takes low values at small areas of y. Then what's going to happen is that xt is going to start from the same point, and it's going to move upwards up to here, but it's going to do so on a different speed. And actually, this shouldn't be a straight line. It should be more of a convex line, because as a function of t, this no longer moves linearly. But effectively, you start from the same point, you end at the same point, but you do so with a different speed. Here, the time has shrunk, because on this area of space, the speed function s takes much larger values. This is the same here as well. You can see that the time has shrunk. Same here. But here, And let's say here you have reached the value 3. So here you have reached the value 3 as well. You start and end at the same points. But here, let's say that these are very low speed areas. So the speed here is quite low. So you can see that this path here for y has expanded for x quite a lot. This is because x traverses this path with a lower speed, so it takes more time for x to move from this part to the next. But in some sense, it kind of tries to follow the same path. It just does so in a different speed. So hopefully this picture kind of makes sense. And the assumptions for our framework that we need to impose is that S is a continuous function. This is mainly technical. It is because we want to define an integral over S, and it is easier to define an integral over continuous functions. At least we can take advantage of the fundamental theorem of calculus to know what the derivative of R is, if this is the case. But also the main assumption, I would say, is that S is integrable with respect to pi. This is very important, and effectively this gives you an upper bound on the way that S can grow. The speed function cannot grow at the tail super fast, because if the speed function grows very fast, the process is going to move so quickly that it's actually going to reach infinity. It's going to explode effectively. This is the idea. This is one way to incorporate an upper bound on what the speed function should be doing. And we also want to impose a lower bound on what the speed function is doing. We lower bound it by some positive value S0. Let's say this is not strictly necessary, but it helps with some of our technical results. What is strictly necessary is that S has to be positive everywhere, because if S, you can imagine if S takes the value 0 somewhere and we happen to go to that point, then we're kind of not going to move around. I mean, we're going to get stuck at that point, and this is not something that we want to do from a sampling perspective. Are there any questions so far? Does it make sense, everything? Like, as always, please, I don't know, write on the chat or something. Let me know if there are any questions. Okay, so what is the connection between X and Y? Well, the connection is that they follow the same path, but with a different speed. However, you can imagine, let's take the unit ball around the origin, and let's say that YT stays on that unit ball 10% of the time or something like that. Well, that might be true, but X does not move around the space with the same speed. So it is not going to spend the same amount of time in that particular unit ball. It's going to spend a different amount of time. And if the amount of mass that X and Y that they assign to the unit ball is different, this means that they have different stationary distributions. They have different limiting distributions. So if you want to target pi using X, then you cannot be targeting pi with Y as well. You need to be targeting something else with Y. And there is a connection. And informally, the connection is that if we want X to target pi, which is our interest, then we need to have Y targeting pi tilde. And pi tilde is given by this formula here. It's basically pi, but you give an extra gravity to values that have high speed, basically. You give this is proportional to S times pi, and this is just a normalization constant just to make everything sum up to 1, integrate to 1. So this is the connection. For X to target pi, Y has to target pi tilde. Okay, so then why might we want to do something like that? We might want to do something like that because let's get back to the multimodal example. Maybe we can put a speed function like this, for example, which has very high speed in this wasteland here and quite a low speed close to the mode. And this means that whenever the process is going to reach an area like this, it's going to move so fast that it has a higher chance of jumping to the other mode effect. This is, on a heuristic level, this is kind of the idea. This is why we might want to impose such a condition. Of course, this is going to create other type of difficulties because we need to be able to simulate a process that has this speed function with this red line here. But on an intuitive level, this is why we might want to do something like this. Cool. And I'm going to present, well, most of the results that I will present, I won't be proving, but I want to prove this first result because it's the bare minimum. It's effectively a law of large numbers. And actually, I think that the proof is quite intuitive in many ways. To do this, we need to make two assumptions. The first assumption is that the speed function satisfies all the assumptions that I had in the previous slide, which is these three assumptions here: continuity, integrability, and lower boundedness. And the other one is that I'm going to assume that the process y satisfies itself a law of large numbers, which I assume that it happens because y, as we have already stated, is your favorite process. You have already studied very well. You know everything about y, so you have proven a law of large numbers. And in particular, you have proven that 1 over t times the integral from 0 up to t of f of y along the path converges to the stationary distribution, to the integral of f over pi tilde. Remember that y has pi tilde as invariant distribution. This is just a law of large numbers. It says that the time average converges to the spatial average, effectively. And this is an almost sure result. So let's say that you have this, then immediately what you're going to get is that x has pi as its unique stationary distribution. And further to that, it also satisfies a law of large numbers, this time with respect to pi. So if you take the integral of f of x along the path of x, this is going to converge to the test function integrated over pi, which is what you want at the end of the day, because if you're a Bayesian, for example, you want to be estimating expectations of this form, expectations of test functions over your posterior, let's say. And okay, maybe you can do this through this quantity here. As t goes to infinity. And I want to show the proof because the proof is very simple. It took us actually 2 weeks to find this proof, and in the end it's like 2 lines. It's a very simple idea, just a change of variables, but I think it's quite, to some extent, I think it's quite educational, and it can give an idea of what's going on, basically. So the idea is that we have this integral here, and we're going to apply a change of variables, u equals to r of t, which is the integral of s. Over x. Now, just very quickly, if we do the du, this is going to be r prime of t dt. This is going to be s at x of t dt. By definition of x, this is at s at y of rt dt. And r of t, we have already said that it is u, so this is s of x of u dt, let's say. So dt, dt is du over s. This is the idea. And then we can write the integral that we're interested in as just by the definition of x, it's y at t. And now we want to create some sort of an imbalance to take advantage of the law of large numbers for y. If we apply, first of all, if we apply the change of variables, u equals rt, we can write this in this form. The dt can be written as du over s of yu. And this is very close to a law of large numbers for the path of y, which we have assumed that it exists, but not quite there because we're dividing by t rather than 1 over rt. So let's multiply and divide by r of t. So we get this and this. And this quantity here, we know that it converges to some particular, to the integral of this over pi tilde, because we have a law of large numbers for u. And the other part, this part here, well, I'm not going to go into many details, but I want you to believe me that this converges to some constant, let's say. Let's not get into too much detail. So this, let's say, converges to a constant. And this thing here, from the law of large numbers of y, it's going to converge to what? To the integral over pi tilde, which is the invariant measure for y, times the test function. And here the test function is f divided by s. So f divided by s here. And if we go one more line, remember that pi tilde is s times pi. So s and s is going to be wiped out, and we're going to get f of y times pi. Times a constant, but actually it's not that difficult to prove that the constant is equal to 1. This is not the main point here. The main point is that effectively we start from this integral and we just apply a change of variables, and immediately, due to the law of large numbers and y, things pop out very naturally. Because we have taken advantage of a time change here. By changing the variables, we inflict a change of time, basically, and we get what we want in the end. Okay, cool. So we also can prove some other results as well that are of more quantitative property. So one result that people in MCMC are quite interested of is called geometric ergodicity. And it tells you, okay, you know that the process is going to converge to the invariant distribution, to the limiting distribution, but you don't know how quickly this is going to happen. So geometric ergodicity tells you that the distance between the two is going to go down exponentially fast. And the distance here is the total variation distance between the law of the process at time t and the invariant measure, basically. You want this to go down very quickly, and we can prove under some suitable conditions that this is the case, that this goes down exponentially fast in time. And even more than that, we can also prove a stronger result that says that if s grows sufficiently fast, you need the speed function to grow sufficiently fast at the tail so that the process moves around very quickly. Then you can even gain something that is called uniform ergodicity. So it's the same result as here, but here the upper bound depends on a function that okay, I should say that this x here is the starting position of the process. I forgot to say that. So in here, the upper bound depends on the starting position of the process effectively. Here, the upper bound does not depend on the starting position of the process. It's completely independent of that. And morally speaking, what does this mean? It means that no matter how bad your initial condition is going to be, the process is going to converge super fast, and it's going to be independent of the initial condition. Why? Because you have such a high speed. That means that you're going to explore the space so quickly that in the end, it doesn't matter where you started from. Even if you started from very far away, it's still okay because you're going to recover pretty quickly through the speed function, basically. Now, I should say that this doesn't say the whole picture, that this doesn't say the whole story, because it could be that if you pick a speed function that grows very, very quickly, it could be that you will create computational problems on the algorithm. So it might be more computational inefficient to run an algorithm like that. But at least in a quantitative level, we know that potentially good things may come out if you pick the speed function large enough. And I'm not giving you all the assumptions here because they're quite technical, and we're going to lose quite a lot of time. And here it's already 4:30 in the evening, so yeah, people are probably a bit tired. Okay, but assuming these things, actually, you can also get immediately, basically, you can get a central limit theorem. So your estimator, this integral estimator that you have here, you can show that not only it converges to the integral of f under pi, but also you can check the fluctuations. It satisfies the central limit theorem. And you can write the asymptotic variance, what is the error of these fluctuations. You can write it explicitly in terms of the asymptotic variance of the base process. Okay, so I just want to show a couple of examples on how time changes would affect particular classes of processes, just so that we can understand what's going on maybe a little bit better. So the first thing is to consider stochastic differential equations, diffusions, let's say. And actually, if you apply a time change on a diffusion, it's going to remain a diffusion, interestingly enough. So let's say that we start from a diffusion that is of this form, a stochastic differential equation that is of this form. This is our base process. It has a drift b tilde, and it has a diffusion matrix sigma tilde, let's say, and this is a Brownian motion. And let's say that you apply a time change with a speed function s. What you're going to get is another diffusion. X is going to be another diffusion. The drift is going to be what was here but multiplied by s. And the diffusion part is going to be what was here multiplied by s to the half. This kind of makes sense because this gives you the linear movement of the SD. And we know that by time changing, we multiply the derivative by s, right? We increase the derivative by s. We go s times faster. So multiplying this by s makes sense. And then the Brownian motion moves in a different time scale. So it has to be s to the half because, yeah, the Brownian motion moves square root of t on a time t, let's say, rather than a linear part t. Okay, and if this one here targets the pi tilde, then we get that this one here is going to target pi. So the next slide is a little bit heavy in notation. You don't have to read all of it. But sorry, I should say that this thing had been studied already by Gareth Roberts and Stromerbark in 2002, but only in the context of diffusions. Okay, so let's say that we have this process here, the xt. Don't look at it very, very carefully, but my claim is that this targets pi. Why? Because this is the time change of an overdamped Langevin. Because it's a time change of this process here, y. You can see that this dx here is s times something plus s to the half times something else. And this something else is this yt here. It is the grad of log of s times pi, this part here, plus square root of 2 of this wt, of this thing here. And it is well known in the literature, this is called overdamped Langevin, this yt here. It's well known that this targets the measure s times pi, whatever is in here inside this log. So this targets pi tilde, s times pi. So by applying a time change with s, we're going to get this, and we know that this is going to target pi, as an example. And let's consider one particular case where we take s of x to be pi to the minus a for some a that is between 0 and 1, for example. What's going to happen in here? Well, what's going to happen in here is that let's focus on the process y for a second. If s is pi to the minus a, this whole thing here is going to become pi to the 1 minus. So this is going to be the dyt. And this means that y is targeting pi to the 1 minus a. Why might this be good? This is called tempering, by the way, in MCMC. Why might this be good? This might be good because if pi is multimodal, typically pi to the 1 minus a is less multimodal. So y is going to be able to explore in a more efficient the target pi to the 1 minus a. And then you can apply a time change to that and recover the right distribution, get back to pi through a time transformation. So pi to the 1 minus a is less multimodal, and here I give you an example of what could happen. The red one is pi, it's a mixture of two Gaussians, and the red one is pi to the 1 over 4. So for example, if you pick the speed function like this, where here is 3 over 4, you're going to get a y that targets this red one. It's easier to target this red one, and then you transfer back your samples through a time change, effectively, to get samples from pi. Okay, the second example is the case of Markov jump processes. So in this particular case, again, this is a closed family under time changing. Markov jump processes will remain Markov jump processes under a time change. And what do Markov jump processes, what they do is that they stay where they are for a random period of time, and then they jump to a new location. So how much time they stay at each point is given by a function r, which depends on the current point. And where they're going to jump when they decide to jump is given by a kernel q. So quite naturally, hopefully, I don't have a whiteboard here. Sorry, I forgot. This is the part where I write something on the whiteboard. But you may be able to see that when you stay constant at some particular point and then you jump from time to time, if you apply a time change to that, this geometric structure is not going to change. You're still going to stay put where you are for some random period of time, and then you're going to be jumping to a new location. And actually, yes, okay, so in the original Markov jump process, you will stay at point y for an exponential time of lambda y, and then you're going to jump according to the kernel q from y to wherever, what the new part is. If you apply a time change s to this one, you are going to jump with rate s times lambda, because you have increased your time, you have accelerated your time by s. So this means that you will be jumping s times faster. So your rate this time is going to be s times lambda. But your jump kernel doesn't change, actually. The jump kernel still stays as they are, because when you jump on the process y stays the same under time changing. The actual jump is not influenced by spreading out or slowing down the time, let's say. And again, if the original process is targeting pi tilde, then the time change process is going to be targeting pi. Okay, cool. Now, why are these interesting objects? These are interesting objects because it's quite easy to simulate them. Because even if you have a very weird speed function s, you just stay constant where you are. So you just need to be able to produce exponential times with rate s times lambda, given the current position, and then you just need to jump according to the kernel q. So it is not that difficult to implement things like that, basically, in practice. It might not be computationally efficient, but at least it is something that you can do. So it's kind of a cute object, let's say, to consider. And the last family of processes that I wanted to discuss is piecewise deterministic Markov processes. So me and Andrea have spent quite a lot of time in studying processes like this, and some other people in MCMC community have spent some time on this as well. This process here that I have here is called the zigzag process for self-explanatory reasons, I guess. This is the path of the process in 2D. This is targeting a two-dimensional target. And you can see what the process is doing. It's moving in straight lines. And actually, it's moving in straight lines that can be, and it can move in 4 different directions. When the process moves in this direction here, it moves towards +1, +1. Here it moves towards -1, +1. Here it moves towards, I guess, -1, -1. And I don't know, maybe here it moves towards -1, towards +1, -1, something like that. So there are 4 different possibilities taken from the hypercube, like plus or minus 1 to the power of 2 here, because 2 is the dimension of the space. And what happened here heuristically? The process moved in straight lines. And let's say that the process moves in this direction towards +1, +1. There are 2 competing factors, 2 competing Poisson processes, that 2 competing clocks, let's say, that are going to tell the process that you have gone far enough and it is time to stop and change your direction. There is one clock that tells the process that it is time to change the x coordinate, the x direction, and another clock that tells the process that it has to change the y coordinate. In this particular case, when the process reached this point here, the clock that told the process change the x coordinate won, because you changed the x coordinate from +1 to -1, but you kept going towards +1 on the y-axis, effectively here. Okay, so yeah, let me give the definition of the algorithm, because this is the main point, but by giving the definition of the algorithm as well, we will be able to see how it changes when we time change this thing. So the algorithm in 2D lives in a space where you have position and velocity. So you are in 2D, you are in R2, this is your position, and this is where you move towards. The position is in R2 and the direction is in the hypercube, ±1 to the 2. It tells you for each of the 2 coordinates whether you move towards the right or to the left, let's say, or up or down. And the process is going to move with unit speed towards the direction that it has decided to follow at that point. So the direction does not change. The direction stays as it is as time progresses, but the derivative of your position, how you move around, is going to be given linearly by v, by the vector v. You move in the direction of v, basically, with a constant speed, let's say a unit speed. And then you have 2 competing clocks, which are given by Poisson processes. The clock A is given by a function lambda1. The first clock is given by a function lambda1, which depends on where you currently are and where you move towards. And the second clock is given by a function lambda2, which again depends on where you are and where you move towards. And these give you some hazard rates, which you can probably see that they are not constant with respect to time. So they change as the time progresses, because they change as the process progresses. They depend on the current position of the process. So these are non-homogeneous Poisson processes, which gives another level of difficulty on how these things can be simulated. But okay, this is what it is. And in order to be able to have this process to target what you want to target, let's say you wanted to target pi, you need to be able to pick the rates lambda I in a very particular way. I don't want you to focus too much on this, but basically it depends on where you move towards and the I partial derivative of the log of pi, effectively. If you think about it a bit, this means that the rate is going to be large when the process tends to go towards areas of lower density, because the process doesn't want to go to areas of lower density, so it has a high rate that tells the process it's time to stop and move around and change your direction. This is heuristically the idea. High rate means you're not going in the right direction, change your direction. Low rate means you're going fine, keep going. And this is given through this quantity here. So both of these Poisson processes are going to create some first arrival times. The first one is going to create T1, the other one is going to create T2. And then you decide which one was the fastest. You take the minimum of them. You pick the coordinate that created the smaller arrival time. You stop at that point. You stop your travel. You change your direction of that coordinate from +1 to -1 or from -1 to +1. And then you start going again. So this thing here is what happened when the process changed the direction in the previous graph. So here is where the clock of the x coordinate rang, and the process started to moving in this direction. And here is when the clock of the y coordinate rang, and you started moving in that direction, basically. Okay, so given this algorithm here, what is going to happen when you time change this thing? Pretty much everything is going to stay the same, except for the fact that this thing here is going to change. You no longer move with constant speed. You move with a speed that depends on the current position. So the xt is going to, the derivative of xt with respect to time is going to be v times s at xt. So this is a scalar and it depends on the current position right now. And this creates an extra level of difficulty in that this is a system of ordinary differential equations, which you need to be able to solve to know where the process is going to be at time t. But having said that, the good thing about these processes, and the reason why I like these processes under a time change situation, is that the base process moves in a straight line, so the x process also has to move in straight lines. And a straight line is an inherently one-dimensional object. So by imposing the condition that xt has to move in a straight line, this system of ordinary differential equations, it's not very hard to, well, if you do the calculations, it's not very hard to believe that actually boils down to solving only one differential equation. Because you only need to know where one coordinate of the process is going to be after time t, and everything else will follow by the linearity, by the fact that you move in a straight line. So solving a one-dimensional ordinary differential equation is not that difficult. It is something that we can do. First of all, there are integrators. You can go to Mathematica and you can integrate this thing. But further to that, you can pick the speed function in such a way so that this thing is analytically given. You can explicitly analytically find out the solution to this. So one thing that you could do, for example, is to take the speed function that is given by 1 plus the square of x. I quite like this speed function here because it grows super linearly. So it moves it forces the process to move around the space quite fast, quite quickly. But also it turns out that given the fact that you move in a straight line, you can explicitly calculate what's going on. So don't pay too much attention to the next few equations. Just focus on the fact that the x1, the first coordinate, you move in a straight line and no changes of direction have occurred. The x1, it can be given analytically, and it grows like the tan of t, basically, up to some constant and some plus parts. It's the tan of t. It grows like the tan of t. And then every other coordinate can be given in terms of the first coordinate here. This is just to say that for this particular speed function, you can explicitly write down what the solution of the ODE is, and you know exactly where you're going to be after time t. So you can simulate, in theory, you can simulate the process directly. Yeah, okay. So I just want to say a couple more things. That as we saw, there are some connections with what it's called tempering or annealing. Because in tempering, this is a classic technique in MCMC, where instead of targeting pi, you target pi to the a as a way to reduce the multimodality of the target, to have something that runs there faster. And as we saw a few slides ago in the stochastic differential equation, by picking the speed function carefully, effectively this is what you're doing. You run y to a tempered target that is less multimodal, and then you get back to the original target through a time transformation. This needs very careful tuning of the temperature A. A here is called the temperature, or maybe the inverse temperature, I'm not entirely sure. And in our case, we need to carefully tune the speed function S accordingly. The other connection is what people have been calling, let's say, either diffeomorphic transformations or space transformations. So the idea on this one is that your target is maybe too complicated, maybe it has very heavy tails. So instead of targeting this one, do a reparameterization effectively, apply a diffeomorphism f to the minus 1 to the state space, go to a new state space, which is reparameterized through f to the minus 1. And there, you need to target the push forward measure of pi under the f to the minus 1, which is given by this. So this is again pi times something else, as is the case for the pi tilde in the case of time chains. So this is the connection, let's say here. And in the concept of applying a space transformation, you apply this, you go to your new state space, you run your favorite algorithm yt that targets this push forward measure y tilde, and then you map back to the original parameterization, to your original target, through applying back the inverse function f effectively. And what you will get out of that is approximate samples from pi. The problems with this approach is that you need to be very careful, especially in high dimensions, on how you're going to pick the diffeomorphism. Actually, not picking a good diffeomorphism very carefully can create quite a lot of problems. It can even induce multimodality out of nowhere, for example. And you might create problems that were not there in the first place. But both approaches effectively are saying, let's run another process on a slightly different target. This is the same case as in time changes as well. And then let's transform the process back to get back to the original samples effectively. Okay, cool. And let me give some semi-practical. Let me explain a bit. Let me give some semi-practical ways of how you can use these time change processes in let's say in practice. This is very raw. It's not. We haven't done a very strong methodological analysis yet, but we're working on this. So the goal, let's say, is that we're trying to estimate the integral f under pi. One thing that you can do is that if you can implement the process directly, as was the case, for example, in the zigzag process with the speed function that I mentioned before, the 1 plus x to the power of 2, then if you can implement this process directly, you can just create this estimator here, 1 over t times the integral 0 up to t of this. In the case where f is a polynomial, this is something that you can typically integrate, especially if x moves in straight lines. But even if you cannot do this, the other thing that you can do is you can say, I'm going to simulate the process as a discrete time process. I'm going to keep the values at time delta, 2 delta, 3 delta, and so on. Delta is up to the user to pick. And you can create the average. You can create the Monte Carlo estimator, the average. And you have a law of large numbers. These things are going to converge where you want. And this, as I mentioned, with PDMPs, this would work quite well. For example, with the zigzag process. And I think this is a good reason to advocate in favor of if there are reasons to advocate for PDMPs, this is one of them, let's say, because they move in straight lines. So it's quite easy to change the time, and it's still quite easy to implement a time changed process in this situation. If you take any k you want, any natural number, k, 0, 1, 2, you can actually simulate this process and you can know where you're going to be after time t explicitly. There are going to be numerical difficulties in deciding what's going on with the Poisson processes, but at least in theory, it's something that you can do, and yeah, because you move in straight lines. Okay, the second approach is that if you take this, you can take advantage of the connection basically between x and y. You can say, I can simulate y, and now I can try to go back to x through a way. And if you plug in here r to the minus 1 of t, after having simulated x, after having simulated y, it turns out that what you will get is this thing here. So imagine for a second that this is just a normalization constant. What is the interpretation of this? The interpretation of this is that I'm going to run y on a different target, on pi tilde, and I'm going to give weight to the samples of y at time t equal to 1 over s. So this has a lot of connections. It's pretty much what people would be calling self-normalized importance sampling, basically, with the importance sampling being 1 over s in this particular case. You give a weight of 1 over s to the sample yt, effectively, and you integrate over this. And if you can, assuming that you can simulate y, which you can, because as we have already established, it's your favorite process in the world. So assuming that you can simulate y, then you can construct this quantity here and you can do this. And even if you cannot, you can take the other approach of simulating y at discrete times, delta 2, delta 3, delta, and so on. And you can construct the ergodic average of these things. And this actually is pretty much what some people did in a paper called Importance Markov Chain. They created a Markov chain targeting pi tilde, and then they weighted it with 1 over s, effectively. Although anyway, their scenario was slightly different to what we're talking about here, I guess. Okay, and one final thing, what you can do is you can take advantage of the nice structure of the Markov jump processes. That is, you can stay where you are for a random period of time, and the random period of time can be given by a rate of s. You picked your s. And then when you decide to jump, you can jump with a kernel q tilde, which leaves pi tilde stationary. How can you do this? You can pick your favorite process in the world that targets pi tilde. You can discretize it, and you can use this discretization as the jump, as the kernel of this jump, for example. And you can do the jumps every time with a rate of s. And it's kind of easier to implement in some cases because you stay where you are and you just have to simulate the exponential random time of speed s. I assume that you can move according to the jump kernel q tilde because this is a process that you have studied already and you know how to simulate from. Yeah, q tilde can be a discretization from your favorite process. Okay, and just a couple of toy, mainly, numerical simulations to finish. This is what happened. We tried to use the zigzag process on a heavy tail target, a two-dimensional student distribution with 5 degrees of freedom. 5 degrees of freedom so that the speed function that we use is pi integrable, which is a main assumption, I will remind you. And if we don't use a speed, in this case, we're going to be confounded in this area here. If we do use a speed, we're going to capture the behavior of the tails a little bit. Of course, in these tails, we're going to move very fast, very quickly. So we're not going to be giving the same gravity to these samples here as we give to these samples here, but at least we can move around the space a little bit more. These two processes have been run for the same computational cost, by the way. And I like this picture because it has different colors. It gives you the colors of the different speed functions. So yeah, it's always quite nice to show to people, I guess. Okay, so another scenario is this time we have a spherically symmetric target, which it has tails that go down faster than any exponential than any polynomial distribution, but they are heavier than any exponential distribution. They go down like e to the x to the half. Okay, and the dimension of the target is 20 dimension. This is the highest dimension that my computer back then could handle, basically. So yeah, in some sense, we can consider this very high dimension. And the speed that we used quite a lot of different speeds. They were all of the form 1 plus a over 2 for different values of a. A is a natural number in this particular case. And we use the zigzag process with different speed functions. And we also used a random walk metropolis, which is another MCMC algorithm. And we used it on a space transformed target. And then we space transformed the samples back just to give a comparison between the two approaches, between a space transformed approach and a time transformed approach. And we reported the effective sample sizes. This is from a previous work of mine. We reported the effective sample sizes either per likelihood evaluations or per minute of computational time. Let me say here that effective ESS stands for effective sample size. It's a quantity that, roughly speaking, tells you how many independent samples has the algorithm managed to produce. So ideally, you want many independent samples from the target. So the higher the value of ESS, the better. And we do it against likelihood evaluations because in many cases, a likelihood evaluation is the main computational cost. And this also is the wall time, the amount of time that the computer had to take to do the simulation. And you can see, I mean, of course, this is not always going to be the case. But at least in this case, it seems like we have gained quite a lot by applying a time changing. And at least compared to the random walk metropolis, with a space transformation, we still gain quite a lot, even though there is quite a lot of computational cost in calculating, in simulating a zigzag process, let's say. So, I mean, this is just to say that you can use, if you have already a process that you really like, sometimes you can use a speed function on top of it, and it could work on a synergy level and it can produce better results, let's say. I think this is the moral of the story to take out of this talk, I would say. Okay, one more thing. Let's say that we have a Cauchy distribution on L2, and let's say that we want to estimate a tail event, the probability that you take a sample from the Cauchy and the sample has norm larger than 150. I think actually, yes, the probability of this is not that small. It's like 1% actually, because there is quite a lot of mass at the tails of the Cauchy distribution. And we used, again, zigzag process with time changing. And the time changing in this case was pi to the minus a. I think actually we used here, sorry, I don't think we used zigzag process. We used the Markov jump process with a particular kernel of jumping around. And we use the speed function that is pi to the minus a, so as to create an element of tempering in some sense, as we saw before. And here we have the median of the relative square error. Interestingly, well, you can see that the red, which is with constant speed function equal to 1, you can see that it goes down quite slowly. And interestingly, it seems like there is some sort of a monotonicity property. The larger the speed function, that is, the larger the a, effectively, the better the performance. This is not a universal property. This is not always the case, but in this particular case, there seems to be some sort of a monotonicity. You need to be taking, here it is better to take a speed function as large as possible. We cannot go much higher than 1/3 because we're breaking the integrability condition in this case. Okay, and one last toy simulation, because we talked about multimodality as well. Here it's a mixture of normal distributions, many mixture of normal distributions. This is the actual target. It's only in 2-dimensional settings, so of course very low dimensional. I'm not claiming that necessarily the behavior is going to be the same in high dimensions. But if we were to run just a zigzag process, starting from this middle here, it would not really understand that there are any other modes. Whereas if you do it with, if you act with a synergy using the speed function of this form, immediately you're going to understand that there are other modes as well, and you're going to explore them. Okay, I think this is it. There are some yes. So yeah, there are some things that we can work in the future. Mainly, how can we find out which one? How can we suggest the best speed function, and how can we try to use this best speed function? We have some ideas on how to go there, but yes, it's not. This is not there yet. Yeah, I would say this is the main thing. And thank you very much for your attention. These are the main references for this work. This is our work. Actually, I have it here if anyone wants to take a look. The paper is called Sampling with Time Changed Markov Processes. It's on arXiv. Yeah, thank you very much for your attention.